Hello, welcome to my channel. This is Mr. Wu, and today I'm here to talk to you about the 2023 VCAA Mathematics Exam 2 Extended Response questions and my solutions to them. First question is a function f. The domain is all of real numbers, and x times x minus 2 in brackets times x plus 1 in brackets, and the graph is shown to you. The first thing I did when I saw the graph and the function was to label some points on the graph. So all the x-intercepts are labeled, and that was quick to do because the rule of the function was given in factorized form. And I've answered the first question also. Say the coordinates of all axial intercepts. The y-intercept is the same as the x-intercept, so that's good. Find the coordinates of the stationary points. This is exam 2, so technically you can do this on your calculator and just write down the answer straight away. But because the question is a two-mark question, we should show some working out just to earn all the 2 marks. So I wrote down the derivative, substituted 0 in for the derivative, and so for x, and it says coordinates, which means you need both the x and y. You need bracket, and you need the x value, and you need the y value, right? So you need not just the x value, you need brackets and a pair of numbers, which are your x value and y value. Next one, you have a different function g, and it's a straight line, x minus 2. Find the values of x for which fx equals gx. So you could just type this into your CAS and solve for it, and you'll get those answers. And write down an expression using definite integral that gives the area of the region bound by f and g. Okay, so this is where I should get my calculator out. So let's define what f is. X minus 2 times x plus 1. Okay, and then define what g is. G is going to be x minus 2, and then I'm going to graph them like this. Okay, the reason I'm graphing them is that I need a definite integral gives the area of the region bound by f and g. So if I can't see the area, of the region bound by f and g, it's difficult to know what function is on top, what function is at the bottom, and what are the terminals of the integral, so the endpoints of the area. So really, the area has 2 parts. One part here where my cursor is, the blue is on top, the red is at the bottom, and the second part where the red is on top and the blue is at the bottom. So, and we have the intersection points already, so that's fine. So the previous question gives you the intersection. So I'm just going to construct the 2 areas. So this one from the first intersection to the second intersection, where the blue one is on top minus the red. So blue minus red is what I want. So that's what I did here. And the second part of it, which is slightly different because it's the red minus the blue. So x minus 2 minus the rest. And then it says find the total area bounded by f and g, correct to 2 decimal places. So all I did was I typed this into the calculator and I evaluated it. So I typed the answer in question 2, question II, and then I wrote down the answer. Okay, and then a third function still, we have a h function, and it's more complicated because you have unknowns in there. X minus a in brackets times x minus b all squared, where h is f plus k, so it is just a translation. Right here, that is a translation. So all we're doing is we're taking f, which is the very original function, the very first function. We take this function, which goes up, down, up, and we translate this in the direction of the y-axis, and we get a different function, which is h. And h is written in a very specific format. It's written in a factorized form with the perfect square. Okay, it's 4 marks, so it's not meant to be easy. But if we ignore f for now and we just consider h and the graph of it, the graph of y goes to h of x. Because it's written in factorized form, I know this. B, 0 is an x-intercept, and it's a turning point. The turning point comes about because it's a square. Right? Anything that's squared is a turning point as well as an x-intercept. And we also, of course, we also have A. A is also another x-intercept. So there are two possible cases here. One is the left-hand side. Right? So if B is negative, A is positive, then the graph has to turn around at B, 0. It looks like this. Otherwise, if B is positive, A is negative, and the graph turns around at B, 0, it looks like this. Now, it's not going to look like this because it's a positive quadratic, right? So it's positive x times positive x and then square. So when your x is a very large number, when your x is a very large positive number, if x is like 1 million, 1 trillion, the square term is going to dominate. And if x is so large, it's bigger than b, it's so much larger than b, then it's positive number squared. So your y value is going to be positive. And if it's so large, then x minus a is also positive, so everything is positive. So your y value should be positive towards the right-hand side, towards the very far extreme right. So we know that it's not going to look like this blue graph I've drawn here. Okay, it's a positive quadratic. Okay, so there's two possibilities, and we need to deal with them one by one. So in the left case, we basically just want to take the original f graph, translate this up or down to get to this, to get to my left case, which really just means translate it down, right? If I translate this down, this turning point is going to come to the x-axis, and that's all I want, right here. I want the turning point to be on the x-axis. And that's okay to do, because if that's the case, I know the x value of the turning point because I did it just here, I did that just here. And so I know what b is. B is the x value of the turning point, which is negative root 7 plus 1 over 3, because I just did that here. Negative root 7 plus 1 over 3. That's the x value of this turning point. And if I translate this down, then x value doesn't change. But how much am I translating? By how many units am I translating down? Well, the y value of the turning point. The y value of the turning point is this number here, 14 root 7 minus 20 over 27. So that's the amount. That's the y value of the turning point is the amount by which I'm translating down. So it goes like this. I take this number, 14 root 7 minus 20 over 27, and I take f and minus that. I minus that exact number to translate my graph down. So once I've done that, I have the value of I have the function, the rule of function h, which means I can then figure out the other x-intercept, which gives me the value a, and that's a calculator step. So I type this function into my calculator and solve for h of x equals to 0 to find a. And then, yeah, I should write that down. So what I did here is I then solve for this, and what I meant to do is this, that, and I got to the end. I got to a equals to this number here. And I'm gonna deal with the other case like this. So h may look like this. which means I'm taking my original f function and shifting it up. But the turning point here is b, and that is this turning point here going up. So the x value doesn't change again, which is root 7 plus 1 over 3. So that's going to be my b value in my second case. But I need to translate this up, which means this turning point has to go to the x-axis. So I need to use the y value of this turning point, which is this number here. So if I just add the size of this, not this is the negative number, so I need to add the size of this number, which means turning it into positive. So I've got this going on. F plus the size of the y value of the turning point brings my turning point up, and from that, again I did h of a equals to 0. Solve that, and I get my a value, and then I get my a value here. Then I get my a value here. All right, question 2. We have a Ferris wheel, if you like, or observation wheel, like this. The center is point P. Passengers are seated in pots, which are carried around as the wheel turns. The wheel moves anti-clockwise. There's an arrow here that gives you the direction. Constant speed, that's kind of important. And completes one full rotation every 30 minutes. As soon as I read that, I wrote down this. Period is 30 minutes. One full rotation is one period, and it's 30 minutes. When a pot is at the lowest point, which is point A, it is 15 meters above the ground, so it's labeled for you in the diagram, so nice. And the wheel has a radius of 60 meters, so that is not labeled in the diagram, so that's what I did. I labeled it in the diagram. So you should translate all information from English sentences into maths, numbers, symbols on a diagram. Okay, and then it says, ignore this writing for now. I didn't write this red line in the beginning. But then I read the question. Consider the function h of t is negative 60 cos of bt close bracket plus c for some value b and c. And it models the height above the ground of the pot. And the pot is originally at A. Originally at point A. So it begins at point A. And it says show that b is pi over 15 and c is 75. So from this equation here, the form of function h, the period is 2 pi over b, but the period needs to be 30 minutes. So I'm going to equate them. I'm going to equate 2 pi over b to 30, and I solve, which is b equals to pi over 15. And then the amplitude is 60. So initially, it's going to be, so without the plus c, if there was no plus c, the graph will look like this. This is 60. Oh, sorry, it's inverted. Without the plus c, the graph is like this, 60 and negative 60. So without the plus c, the lowest point of the Ferris wheel, the observation wheel, is negative 60, but I need the lowest point to be 15. The lowest point, because that's what h measures. H measures the height above ground. So the height above ground, the lowest height is not negative 60. The lowest height above ground is positive 15. So I need to do this. C is a translation, so I'm moving this up by c units. C is a translation. So negative 60 plus c has to equal to 15. The lowest point, translate up by c units, has to be 15. And therefore c is 75. And I wrote this down. Once I have all the numbers for b and c, well, I mean, the question gives you that anyway. I rewrote the function h completely, negative 60 cos pi over 15t bracket plus 75. And then it says find the average height. Average is an important word. average height of a part on the wheel as it travels from A to B. A is here, B is here. B is a quarter way up, not a full circle, a quarter circle. Give your answer in meters correct to 2 decimal places. Well, it's average value, so hopefully you remember the formula to find average value. If you have an integral going from A to B and fx dx, you need to do this. So the average value of a function from x equals to A to x equals to B is the integration of that function and divided by the difference between B and A. It's like again, you will never memorize formula. You will just understand it. So the integration gives you the area, but our job is to turn this area into a rectangle, something like this, something like this. Turn this area into a rectangle, and the height is the average value. Average value is the height, which means you take the area that is not a rectangle, that is in fact not a rectangle, and you pretend it is a rectangle, you divide by the length here, and you get the height. And the height is the average value. Okay, so for us, the average height is written in terms of t. T is time, right? So at point A, t is 0, so that's kind of okay. T is 0 at point A because that's the start. But what about B? How much time is it? When I get to B, what's the time? Well, to go full circle, it's 30 minutes. So to go a quarter circle, 30 over 4. To go a quarter circle, the time it takes is 30 minutes divided by 4. So really, where is my stylus? Really, at point A, t is 0. At point B, this is the time. 30 minutes, one full circle, but I'm only going a quarter circle, so divide by 4, which is where the 15 over 2 comes from. And we type this into the calculator and get the answer. And then find the average rate of change in meters per minute of the height of part of the wheel as it travels from A to B. So again, you need to know the definition of average rate of change. Not just the average height, but the average rate of change, which is not the instantaneous rate of change. The instantaneous rate of change is just the derivative. So here, the average rate of change is a straight line, basically, in the graph. So the cost graph goes like this, and we are just concerned with a straight line, like this, and the gradient of the straight line. So y value minus y value over x value minus x value. That's the gradient of a straight line. Average rate of change is, again, you have a curve, you have 2 points, and you have a straight line in between, and the gradient of the straight line. Rise over 1, rise over run, y minus y, x minus x. And that's the answer. Okay, after 15 minutes, the wheel stops moving and remains stationary for 5 minutes. After this, it continues moving at double the speed for another 7.5 minutes. The height above ground can then be modeled by this. So for the first 15 minutes, it's just modeled by h. And then between 15 and 20 minutes, it's not moving, so it's the same constant height, which is some k value. And after that, between 20 and 27.5 minutes, it's a different speed. And then k and are positive, and is real number. Okay, so k is the height at 15 minutes. So all we need to do is substitute 15 into h to find the height, and that has to be k, because k is the height after at 15 minutes. And m, in terms of m, it's like this. So I've written it here. If I sub mt plus n into h, I get this sort of thing going on. And so basically, if the speed is double, it means the period is half, right? Period RIOD is half. Because if the speed is double, the time it takes to go through the same distance should be halved. So going through one circle, one cycle, one revolution, that the time it takes should be halved because the speed is not doubled. Which means the period should be 15 minutes. But if you look at the function itself, the dilation is m pi over 15. Okay, so the period is that. Because the dilation is pi over 15 times m, so I need to take 2 pi and divide by the dilation. Yeah, I shouldn't put that there. I should just write this down. Yeah, that's what I should write. Okay, so the coefficient of t, basically, the coefficient of t is m pi over 15. The coefficient of t is m pi over 15. So the dilation is the reciprocal of it. So the reciprocal is 15 over m pi, which means the period is the original period of cos t function, of a simple cos t function, is 2 pi. So 2 pi times 15 over m pi, the dilation has to be 15 because that's the period I want. And if you cancel things out, what am I gonna 2 over m is 1, right? 15 go away, pi and pi go away, 2 over m is 1. So m is 2. Okay, find all possible values of n. All this is the two functions have to connect. The k function and the h bracket mt plus n close bracket have to connect. And since I know what m is, I can put that in. So h bracket 2t plus n, and I'm defining this as a new function because that's not in the question itself. If what I'm about to use isn't in the question, I have to define it myself, which I did. And I know that I know that when t is 20, the third function has to start where the second function ends. The third function has to start where the second rule ends. So, which means when t is 20, my a function, which is really the third function, has to be 135 because that's what the second function is. The second function is 135. So the third function has to be 135 when t is 20. And I sub this into my calculator, and I get this answer here. It says all possible values, and of course it's a trigonometry function, so there are many possible answers. That is an integer. And then I have to sketch the graph, which just looks like this. You could do this by hand, but you could also do this with your calculator. And to do this, you just have to pick an n value. Pick the easy one. So that is an integer, so just make it 0. So 5. 5 is n value. So sub that in, and you should be good to go. Actually, let me show you exactly what I did. If I got. So let me put in the h function. This one here. negative 60 cos pi over 15x plus 75. Yep. And then I need my w function, which is a hybrid. This. And first, it starts with this. Zero between x and 15, and k is 135, 15, and 20, and then I have h, but m is 2, and 5, and that's done, and I'm ready to graph. Window A, and that will fit. That's not even really fitting that much. 150, changes to 150, and let's change this. I know what this is. This is gonna be 29, let's say. 29. And here we go. And you're just gonna copy this onto your paper, and it should look something like this. And just label the points in. And be careful with the endpoints. The endpoint is inclusive. 0 is including in t, and 27.5 is included in t. So make sure you do a solid dot on both ends. On either end, on both ends, you do solid dot, and then the connection points between each part of the hybrid function. Okay. And of course, this is a grid line, so you have to match your numbers to the grid. Okay, function g, no restriction on domain, 2 to the power of x plus 5. What is the limit of g as x goes to negative infinity? Right here. So if you really want, you can draw this with a calculator, but to draw this by hand is a really quick job. So like this. That's what it looks like, exponential function. So if x goes to negative infinity, the y value should approach 5. And then the derivative g dash can be expressed in this format. Find the real number k. Well, that's a calculator question. You can differentiate any exponential function by hand. There is a formula. There is a formula to differentiate any exponential function with any base. The base doesn't have to be e to the power of x. The base can be any number, any real number, and you can differentiate. There's a formula for it. You will learn it in uni. But for now, that's not really part of the slide design. So differentiating exponential function with a base 2 with a base other than e is not in the slide design, but it's totally doable. It's not that hard. But assume you don't know, and that's a good assumption because it's not in the slide design. You can differentiate using calculator, and you see something times 2 to the power of x. That something is log e2, like that. Okay, let a be a real number. Find, in terms of a, the equation of the tangent to g at the point a, g, a. Well, the answer looks very long, but it is just tangent to the function g at some point x equals to a. Manual calculus, number 9, tangent line. So tangent line gx, x equals to a. That's it. And you copy this down. There's an x term here, so x to the power of 1, so it's a straight line. So gradient times x, so straight line, minus constant. Everything is in a, there's no x anymore. So it's a straight line function, it's a tangent function, like this. Hence or otherwise, let me actually go back. I do want to comment on something that I saw here. See this question, where it is. This question says, hence or otherwise, find the equation of the tangent to G that passes through the origin correct to 3 decimal places. If you couldn't do CI, it's very difficult to do CII. VCAA tells you so, hence, it does say or otherwise, but I'm not sure any other way is easy. Any other way will be very difficult, I imagine. So it's either you can't do CI, but then you somehow find a very complicated and complex and difficult way to do CII, and you could still get it. But chances are, if you couldn't do CI, then you couldn't do CII. So you don't. It's very difficult to get consequential mark, and you get 3 marks taken off all of a sudden, just because you can't do CI. Same thing here. Same thing here. Where am I? Yeah, see here. So state the values of K and M. You have to find M. And if you didn't find M, it will also be very difficult for you to find N over here. So if you couldn't find M, you lose the 1 mark. But then you will also most likely lose the 2 marks, because without M, you can't find N. You may get consequential marks here, but to me, this is still a bit problematic. Here, they've done the right thing, so show B and C is those values, and then even if you can't find B and C, you can still use them to do question B and question C. So maybe that's something that should occur throughout. If a subsequent question depends on the previous question, then the previous question should be a show question or a verify or a or somehow there's a hint given somewhere. Okay, but let's look at this. So assuming you have the tangent rule, and again, if you didn't, C2 will be quite difficult. You need to find the equation of the tangent that passes through the origin, correct to 3 decimal places. Pass through origin. So the tangent line has to pass through origin. This means y-intercept is 0. I should put 0, 0. The y-intercept is 0, 0, which means this should be 0, the constant term. The constant term in my tangent rule should be 0, and that's all I'm doing. I take the constant term in the tangent line rule, make it equal to 0, solve in calculator, A is this. And I sub this A back in, so to the power of A log E2, because I need to write down the question is not asking for A, the question is asking for the equation of the tangent. So I still need to sub A back in to write 4.255. And by the way, this language is kind of problematic also. You cannot find the equation correct to 3 decimal places. You can only find a number correct to 3 decimal places. Right? So if you read the question, if you simplify the sentence, it says find the equation correct to 3 decimal places. Essentially, that's what it says. But that's not the right wording or phrasing or language or grammar. You cannot write an equation correct to 3 decimal places because it's got equal sign, it has y and x, it has pronumerals, it has letters. You can only write numbers correct to 3 decimal places. So the question should have been worded something like, find the equation blah 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 and express all constants correct to 3 decimal places. It should, like before it says correct to 3 decimal places, it should say express or write constants correct to 3 decimal places, not the equation itself. Okay, let h be, well, there's no domain restriction, and the function rule is 2 to the power of x minus x squared. Find the coordinates of the point of inflection for h corrected 2 decimal places. This is a bit weird, this question here. When VCAA published the new study design, it was explicitly mentioned that using double derivatives to find coordinates, exact coordinates of point of inflection, will not be necessary. It is explicitly not in the study design. Yet it appears in this exam question. There may be ways to find the point of inflection, the exact coordinates of the point of inflection without double derivative, but I don't see how that's easy to do for 1 mark question. Like for 1 mark question, I don't see any easy way to avoid double derivative to find a point of inflection. And so that's what I did. I did use double derivative I make it equal to 0 to find the exact coordinates of the point of inflection. This only gives you the x value, and then you sub it back in to find the y value. So I'm not sure what the intention of the question writer was. Was the intention, when the person was writing this, was the intention to use double derivative to find point of inflection? If so, then we have a problem because it's not in the study design. If not, I'll have to see the examiner report before I know exactly what's going on. Okay, next question. Find the largest interval of x value for which h is strictly decreasing. Give your answer correct to 2 decimal places. Largest interval, that's an important word. So, let's have a look. H is h. Yeah, 2 to the power of x. No. Minus x squared. And I'm going to graph this now. Right here. So you can see it goes up over here, and it goes up on the left as well. So there's this little part in the middle where, does that work? Yes, that works now. There's this little part in the middle where the graph goes down. And the question says, correct the 2 decimal places. Oh, sorry, that's not what I meant. I meant for which h is strictly decreasing. It's decreasing. So it's from this turning point to this turning point. And, well, you could do this. You could do this, but I would suggest not. And you can do this, analyze and minimum. You can do this and look at the x-intercepts. X coordinates, but that's not my suggestion. The graph function on CAS and the subsequent analyzed graph functions, all of them, they don't always give you the correct answer. They too often, I think, not that frequently, but it's one too frequent, one too often, once too often. Often it gives you wrong numbers because it's not really doing proper algebraic calculations behind the scene when you're in the graph function. I'm not sure exactly what, but they're either using some sort of floating point approximation, or even worse, they're using pixels to pick points. So my suggestion to you is always to go to the calculation page and find the turning points that way. You take the function and you differentiate, and you make the derivative 0 and you solve for x. So my suggestion is always to do algebraic calculation in the calculator to find the coordinates of the turning point. So almost never rely on coordinates given in the graph function. It just gives you an indication, but to get the exact numbers, you should use the calculator page. And that's it, 0.49, 3.21. 0.49, 3.21. And largest interval, which means the 2 points are included. You should include those 2 points because strictly decreasing, and here's the keyword, strictly decreasing, doesn't care about derivative. Don't care about derivative. It only cares about 2 points. Within the interval, 2 points, you can pick any, within the interval, you can pick any 2 points. You can pick any 2 points. And a larger, as long as the larger x value gives you a smaller y value, then your interval is strictly decreasing, which means you should include those points, right? Because if you include the turning point and the turning point, right, if you include them, it just means you can pick those 2 points. Right? You can in this interval you can pick those 2 points. You can pick the turning point and you can pick the turning point, and you check, is a bigger x value going to give you a smaller y value? And the answer is yes. Therefore, those 2 points should be included in your interval here because you want your largest interval. Next, Newton's method. Initial estimate is 0, and I need to write down all of x1, x2, x3, x4, and so on. So again, if you forget Newton's formula, Newton's method, sorry, it's right here, right about here, but you should memorize it by now. So I'm gonna define a derivative of h, which is just this, and then Newton's method, I'm going to define that also, x minus h over dh, and then I can use Newton. So Newton is here, 0 comes first, wait, so that's the first thing I write down. So when x is 0, and I don't need to write this down, do I? X naught 0, yeah, that's right. So x naught is 0, and the next x value is then going to be my answer here, negative 1.443. So I write it down here, and then I put this in, actually, yeah, I should put that in. Good. And so this is the number I put in next, negative 8.9, 0.897 and so on. 3 decimal place, yep. And then this becomes my x2, and then so I sub that in to get x3, and so on. So I'm going to sub that in, but always use the exact value, and that's my final answer. And then for the function h, it explains why the solution to the equation, this thing, should not be used as an initial estimate in Newton's method. Okay, so slightly tricky question, because first thing you need to notice, and it's not that easy to notice because, let me do this. So h is this, remember, to the power of x minus x squared. You need to kind of notice the derivative of h is log e2 times 2x minus times 2 to the power of x minus 2x, which is, if you put that in your head, which is this. Log e2 times 2 to the power of x minus 2x. Log e2 times 2 to the power of x minus 2x. That is the derivative of your function, of your h function. So it's saying why solving the derivative equals to 0 should not be used as an initial estimate. Well, if you did that, the solution to the derivative equals to 0 gives the turning point on the original graph h, and the tangent at this turning point does not cross the x-axis, so Newton's method breaks down. Let me show you what I mean by that. So first of all, please recall Newton's method is used to approximate the x-intercept. So what happens is you pick some off value that's off. You pick some x value that's not the answer. You go to that graph at that x value and you draw a tangent. And you have the x-intercept of the tangent. So this is x0, and that becomes x1. And you go up to the graph, you go to the dot on the graph, and you draw another tangent like this, and the x-intercept of the tangent becomes x2, and so on. So you can see x0, x0, x1, x2, x3, x4. Eventually, you keep drawing tangent, and you keep finding the x-intercept of the tangent. You are going to get very close to the x-intercept of your original graph. Okay, so let's say this is h. But if you begin your x0, let me actually draw an x-intercept. If you begin your x0 here, exactly at the turning point, you can draw a tangent, but it has no x-intercept because it doesn't go through the x-axis. It's a horizontal line. The tangent at the turning point is a horizontal line. So without the tangent going through x-axis and therefore not having a x-intercept, Newton's method doesn't work. Newton's method means you have to find the x-intercept of a tangent, but there's no x-intercept for this tangent, so it doesn't work. So if we use the solution to derivative equals to 0, it means we are using x0 where the turning point is, and that's not good for Newton's method. Okay, here's my comment for question H. This is a fire question, and I'll explain why. It is super fire, this one. There's a positive real number n for which n to the power of x minus x to the power of n has a local minimum on the x-axis. Find the value of n. Local minimum on the x-axis. The graph has to behave like this. There's one behavior like this. Okay, there is a local minimum on the x-axis. Okay, this is a fire question because I tried for so long. I spent maybe 30 minutes, could be more, on this question, and I tried many different approaches, many different things, many dead ends, before I finally arrived at something for which I'm satisfied. So for our question, it took me a long time. It took me many tries, many attempts to get to the answer. First, hopefully, you realize it is very difficult to have any clue about this question. So the best thing to do is this. I'm gonna, why is n has been defined on the outside the, and I do this. Action, delete. Actually, I'm just gonna clear everything, hang on. Clear everything. So now n is nothing. Yeah, good. Okay, so the function is f. I'm going to define it in terms of nx. And I get x to the power of n like this. And my beautiful slider is going to come into play. Slider. Here we go. Wait, that's not what I'm. Okay, here we go. So the slider is working. So is there any restriction on n? Yes, n is a positive. There's bound to be some restriction. If it's negative, then it's very ugly. It's not even a function anymore, I imagine. Okay, positive real number, and it's positive. So let's do it. I have a slider here. I need the local minimum to be at the x-axis. Well, here n is 2 here, which is what the previous question was. N is 2. So 2 to the power x minus x squared. So the question has already taken us to deal with n equals to 2. Right, n equals to 2. And the problem for us is the local minimum is not on the x-axis. Start with 1. That's not good. That looks like a straight line. 1.6. No. Let me actually change this. Change this to 0. If it's less than 1, does it work? Yeah, it does work. Well, there's a graph there, but it does not a local minimum. It will just go on forever. What about 0.88? No, still doesn't work. There's no local minimum. Something like this. Yeah, it looks like a straight line now. And then, so let's try 1.5. Looks like there's a local minimum, but it's not on the x-axis. So you keep playing, and that's what I did. I basically just play with it. You can see the local minimum going up. Right? As I increase n, the local minimum is going up. And 2, we did that before, didn't work. So 2.2, yeah, getting close. The local minimum is getting close to the x-axis. There's another one here, but that one, I don't think it ever goes anywhere. Yep, there's nothing here. So 2.2, not there. Neither local minimum is on the x-axis. 2.3, you can see I'm getting close now. 2.4, 2.5, 6, and I'm basically there. 2.6, 2.7, I'm basically going there. 8, still very close. 9, and I'm coming back down. So, and the local minimum moves away from the x-axis as I increase. So the local minimum, and let's try 5 even. Oh wait, the entire thing. Okay, so you can see. Does that work? Yeah. Yeah. So you can see the local minimum is on the x-axis around this point. Around n is 2.7. So you know the answer you're looking for is something like 2.7 or 2.8 or 2.6 or something in between. So that's the first thing I did, which is very hard, took a long time. And then I tried so many things. And this is what I ended up with. So I take f and I differentiated it using calculator. So that's just a calculator crunch. And then I said to myself, I need those conditions. I need n and x to work like this. I need some x value that gives me a 0 y value because I need this point. Basically, I'm saying I need to find this point. I need to find the local minimum. This local minimum is also the x-intercept. I need to find this x-intercept, which is also a turning point. I need to find this point, the coordinates of this point. So, how do you find the coordinates of this point? Well, this point has to be whatever x value you sub in, the function gives you a 0 y value, and the x value when you sub it in, the derivative is equal to 0 because it's a turning point. So the x value for this point has to satisfy both conditions. When you sub it in, the f value is 0 and the f dash value is 0. The first condition gives me this. The first condition gives me this. If I put 0 on the left, equals to n to the power x minus x to the power n, which means I can bring the negative x to the power n to the left. And then I stared at this for a very long time. I stared at this for a very long time. N to the power of x equals x to the power of n. The relationship between them is just the switching between n and x, right? So n is the base, x is the exponent, and over here it's a simple switch of the places. So x becomes the base and n becomes the exponent. I looked at this for a very long time, and then I thought, well, this equation will hold if n and x are the same, right? Because you have one number raised to another number, right? So let's say you have 5 to the power of 2, and if you switch them, it's 2 to the power of 5. Clearly, they're not equal, right? You can also do like 3 to the power of 4, and then compare that to 4 to the power of 3. Clearly, they're not equal. So for this to work, for this equation to work, n and x have to be the same, and that's what I wrote down. I wrote down n equals to x. So that's the first conclusion I made from fx equals to 0. And then the derivative has to equal to 0. So replace f dash with 0, move the negative n times x to the power of n minus 1 to the left. I get this. But I'm skipping a few steps here. I take this. That's the ugly thing. The power here, the exponent is too ugly. It's n minus 1. So I change this into n x to the power of n x to the power of negative 1, because it is, right? I'm breaking the exponent into two parts. X to the power of n times x to the power of negative 1. And then that's equal to ln of n to the power of x, n to the power of x. But where am I? X to the power of n is equal to n to the power of x. Right? That's what I said before. I said before that n to the form f of x equals to 0. I have to have this equation hold true. X to the power of n is n to the power of x. So that's all I did. I took this and I replaced it with n to the power of x. So that's my next line. My next line is n times n to the power of x and times x to the power of negative 1 equals log n of n times n to the power of x. But I have this and this common factor, so I divided them. So all I have now is n over x equals to ln n. So x is going to be this times x on both sides and divide ln n on both sides. So I get this. And then I take this x equals to n over ln n. Again, by the way, ln is the natural log of base e. Sub that in, so I get n equals, I took this equation, sub it into the left equation, so I get n equals to n over ln n, which means natural log n equals to 1, which means n is e. Right, this is really that equals to 1. And so you convert the logarithm into an exponential again, so e to the power of 1. There's a 1 here. E to the power of 1 is n. And that is my answer. N is the Euler's number. Remember, E is Euler's number. Let's try it. E. Here we go. When I change the slider to E, n value to E, my local minimum is exactly the x-intercept. See the y value here? The y value is 0. This point, x-intercept, sure, but it also is the turning point, the local minimum. And that's it. And of course, E is 2.71 something. Hopefully, you know that, 2.7182 something.